Okay, the next section is section 5.3, classifying triangles. I'm going to introduce a bunch of different types of triangles, which you should already be familiar with. There's really not too many difficult problems in this section, but I'm going to save the one type of problem that is tough for the end of this video. Okay, so classifying triangles, the first two problems on this worksheet are actually problems from the previous section. They're just some longer proofs. Both are good proofs for you to go ahead and try. So I'm actually going to ask you to flip to the next page. So at the top of the next page is just a rundown of material that you need to know from this section. First thing is a scalene triangle. That's basically just a triangle that has no sides congruent to each other. Isosceles triangle has two sides that are congruent to each other. Call those sides legs. The bottom is the base. The top is what we call the vertex. And of course these each would be the base angle. An equilateral triangle is when all the sides are congruent to each other. An equilateral triangle is also what we call equiangular. So all the angles are actually congruent to each other also, 60 degrees. Okay, and we know that they're 60 degrees because the three angles of a triangle add up to 180 degrees. I think you all knew that. An acute triangle is a triangle that has all angles that are less than 90 degrees. Right triangle, of course, has one right angle. These are the legs. This is the hypotenuse. These could be congruent to each other if it's isosceles. An obtuse triangle is a triangle that has one angle that is greater than 90 degrees, but less than 180. Okay, side lengths versus angles. So if I have a triangle where my side lengths are 10, 9, and 8, for example, let's call it triangle ABC. The side that's opposite of, well, the angle that's opposite the biggest side is going to be the largest angle. So in this case, angle C is the angle that's opposite of the biggest side. So angle C is going to be bigger than the next one is going to be angle A, because that's opposite of the 9. And then, of course, angle B is going to be the smallest angle. Okay, and one more quick concept that I'm going to throw at you. It may pop up again later, but basically that concept is, well, let me ask you a question first. Can I have a 3, 4, 100 triangle? So 3 inches by 4 inches by 100 inches, for example. And hopefully you can see that you can't. This side is going to be way too big for these two original sides, the 3 and 4 sides. And so there's a limit to, there's a restriction on that third side given the first two sides of a triangle. So the limit's going to be basically this. The third side has to be less than the sum of the first two sides and greater than the difference. So in this particular example, it has to be bigger than 1 but the third side has to be less than, but it can't be equal to 7. Okay, hopefully that makes some sense. I'm going to jump actually to the third page right now and go over a couple of proofs that have to do with some of these definitions that we just talked about. So we're working on page 3 right now. This is the proof, and it has to do with some of the material that was introduced on the second page. The first thing you'll notice is that this is a triangle that's isosceles, and so we know that an isosceles triangle, we know that it has two sides that are congruent to each other as well as the two base angles. It's saying that the other given here is saying that CD and BE bisect the base angles, so we know that these are the base angles, and because they're base angles we know that those are congruent to each other as well as the two legs are congruent to each other right there. We know that there's two bisect statements, and that tells me that I'm probably doing something with multiplication or division property, and I'm going to need these base angles to be congruent to each other, so it's going to be division property. So my first step here will be triangle ABC is isosceles. My second step here will be that angle ABC is congruent to angle ACB, and the reason is going to be because if it's an isosceles triangle, then the two base angles are congruent to each other. Okay, so that's how you use that in a proof, and the proof itself is not that difficult, so I just wanted to show you that. The next proof also has the same type of situation going on. It says that MW is congruent to WS, or this one's congruent to this one, sorry about that. And it says, which means that it's an isosceles triangle. So I know that this base angle is going to be congruent to this base angle. And I know that this is a bisector, and this is a bisector. So again, I'm looking at multiplication or division property, probably the multiplication property, since 3 is the one congruent to 4, the smaller angles are congruent to each other. And so I'm going to start with NW being congruent to WS. Step 1, that's given. Step 2, you know it's an isosceles triangle. So triangle NWS is isosceles, and the reason would be because if the sides are congruent, two sides are congruent, then it's an isosceles triangle. And because it's an isosceles triangle, I know now that angle 3 is congruent to angle 4, and that's going to be because if it's isosceles, then the base angles are going to be congruent to each other. What we're going to find out in the next section, just a little preview, is that we can go straight from this step to this step and skip this step entirely. Okay, but for this section right now, go ahead and have all three parts within the proof. Okay, the rest of the proof again is not that bad. You just prove some triangles congruent. I'm going to move actually back to page 2 because I want to hit the problem that is the tough problem from this section. Okay, we're back to page 2 here, and we're looking at what's called the exterior angle theorem. So the exterior angle theorem comes from this. You know that these two angles here are congruent to each other. Are supplementary to each other. So angle 1 plus angle 2 is equal to 180 degrees. We also learned in this section, we already knew, that 2, 3, and 4 also add up to 180 degrees. So hopefully you can see, because this stuff is exactly the same, that angle 1 here has to be the same, or has to be equal to, angle 4 plus angle 3. That is what we call the exterior angle theorem. Basically, it's that the exterior angle of a triangle is equal to the sum of the two angles that are furthest away, like a remote control, two remote interior angles that are on the inside of the triangle. So the exterior angle of a triangle is equal to the sum of the two remote interior angles of the triangle. So this angle is equal to this one plus that one right there. Okay, so we're going to move on to this next problem. We need to use the exterior angle theorem for this problem. And usually what we do in class is we will spend probably 20 minutes doing this problem. And so what I'll do is I'm going to introduce it, and I'm going to ask you to pause the video and take some time and try to figure this problem out. So in this problem, it's given that this whole side is congruent to this whole side, so it's an isosceles triangle. I also know that AE is congruent to DE, which is congruent to DB, which is congruent to BC. They're all congruent to each other, which means you got a whole bunch of isosceles triangles there. What you're supposed to find here is all the angle measures. Okay, and that's it. That's all the given information. So at this point here, if you could turn off the video or stop the video, and then after you try it for a while, hopefully you'll get it. If you don't get it, then go ahead and we'll go over it together. Okay? So take some time. Okay, we're back now. Hopefully you got it. But basically, you want to start by putting X right there. So X is going to be starting right there. Because that is your X value, you also know that this is also X. If you focus on just this triangle here, you can see that it's an isosceles triangle where the two X's are the base. Now, here's the tricky part. If I focus on this triangle, the exterior angle for this triangle is right over here. And so the value of that exterior angle is equal to the sum of the two remote interior angles. And the two remote interior angles are the two X values, the two X's. So that means that this angle has to be 2x. Now, bring your eyes over to the next triangle here, and that triangle is also isosceles. So that means that if this is 2x, then this down here also has to be 2x. Those are both base angles of an isosceles triangle if you kind of flip the sheet of paper over. Next, if I focus on, let's focus on the next triangle here. So if I focus on this triangle right here, and extend this out, this angle right here is the exterior angle for the blue triangle. So that means that the exterior angle is equal to the sum of the two remote interior angles. That would be this angle and this angle. So that means that this exterior angle is equal to 3x. And now bring your eyes over to this triangle right here. And so that is also an isosceles triangle with these as your sides. This is the other base angle, so it's got to be 3x. And now if you focus your eyes on the entire big triangle, you know that this side right here is equal to this side right here. So the two base angles have to be equal to each other. This angle and this angle must be equal to each other. So therefore, this has to be 3x. So that means that has to be x. And now I can use the fact that the three angles of a triangle add up to 180. And I can just take this orange triangle down here, or the big triangle all the way around, and I can do 3x plus 3x plus the vertex angle, which is plus x, is equal to 180 degrees, or that's 7x equals 180 on the calculator. X is equal to 25.71, and then just plug it back in to find all the different angles there. Alright, I hope you found that to be a fun problem. That is a very legit 4-level problem. We actually do this quite a bit in 4-level, so hopefully you enjoyed that. Okay, take care.